Yo, what is up, guys? Welcome back. Oh, episode 96, I think, today. Yep, 96. Take a look at a drowsy today. Drowsy Pokemon. Oh, we need the sound, dude. Jeez. Look at this guy, man. He's like an elephant cunt. That's our sound for the day. I'll do it one more time. There we go. What a great sound. I don't understand why we got a frost advisory today. That's cool. All right. Let's take a look at our problem of the day. Count good triplets in an array. Got a hard problem. Should we take a read? Maybe we shall. Given a zero index, raise nums 1, nums 2, and the length of n, both of which are permutations. Do I want to do this problem? We're going to skip this problem. I just don't want to commit to something like that yet. Let's take a look at this guy's Leetcode post, man. Where was it? BlackRock Alpha. What is this? Anonymous user. Interesting. Okay. Where are we at, man? Take a look at Nico's roadmap. Let's start today with closest points to origin. Closest points to origin. They return the answer in any order. The answer is guaranteed to be unique except for that order that it's in. So we're given some points. Return the k closest points to the origin. So we want the closest point to the origin here. The distance between 1, 3 is 10. The distance between 1 is 8. Since 8 is less than square root of 10, negative 2, 2 is closer to the origin. We only want the closest k is equal to 1 point from the origin, so the answer is just negative 2, 2. 2, we'd have multiple. We want to return a list. A list inside of a list. Interesting. So I believe this is a min heap here. I don't know if it specifically says that. No. Can't solve this using a min heap. Heaps in Python. Import a heap. Put heap queue. Dude. Okay, import heap queue. Ooh. Priority queue of log n time to heap. Okay. I can see why this is a heap problem because we're looking for like okay. What we want to do here? We want to create a heap queue, right? So probably should go to our documentation. Let's create a reservoir, right? We want to go, okay, well, for point in points, right? Let's print out point. We want to heapify this first, though. So let's do heap is equal to, would we do like heap q dot heapify? We would heapify our points variable, right? Okay. Can we make this equal to something like heap? If we print out heap. We print none here. Man, I have to look at our problem yesterday, dude. I cannot remember how we assigned the freaking heap, dude. We have to copy the array first. Min underscore heap. Nums is not defined. Oops, this is meant to be points. Still getting none here. Why are we getting none? Man. Why is this giving a null array? Min heap printing null. You're seeing none printed because of this line. The function heapify modifies the list in place and returns none. So when you do, you're assigning none to min heap. Oh my gosh, dude. There we go. Okay. How does this assign a min heap? I wonder if it's actually doing anything. Can a min heap okay, it compares the first element. Well, wouldn't -2 be? What way? Lexicographic order. It's because we're not actually using the heap here. This needs to be min heap. Okay, now it's working. Okay. I guess technically the let's try it. Let's go. Okay, well, for point in min heap. I guess while k is greater than 0, let's try this, right? Because we have a k. See if this works. K is greater than 0, we pop the min heap, right? So we would go, okay. Point is equal to heap q dot heap pop. Passing our min heap, right? We print our point. Let's see what this gives us. Just gonna give us an infinite loop. Index is out of range. Index is out of range. Is that because points could be none? Why are we getting index error? This line, because min heap has become empty before k reaches 0. Maybe we want to min heap the point instead. Right? So we could let's call this like points, right? We go for, so, let's call it real points. For point in points, right? Well, AB is equal to point. Okay, then we do, okay. Ands is equal to square root of x1, x2. x1, x2. x1, x2, but we only have 1 point though. Like, what? Are we comparing 2 points? Okay, closest points to the origin. Okay. So x1 would be 0. Or do we do... Okay, I think that, well, they say x1, y1 is the points, right? So we would go, okay, well, a minus 0 squared okay, right, squared plus y1, which is b minus 0 squared, we need a square root, from this we want to return, okay, we want to just, and dot append real points, sorry, real points dot append ends. Point ends, and we would go, okay, we would want to print ends. Unsupported types, dude. What the hell? Well, I guess doesn't the square root remove? I guess it's x squared, right? Because technically we're comparing it to a 0. So 0 minus something is a 0. So we go x. Is it? Maybe it's a times a plus b times v. Output null. We want to output our real points. Let's see. Well, technically we have the answer here, right? We would have square root 10, square root 8. Okay, square root 8. Square root 6 is 2.44. 4 is 4. Square root 2 is 1. 1 is 1. Square root 0 is 0. Square root negative 1 I. Okay, so you can't square a negative number. But we can have... Okay, we're going to keep it for now. I think we're meant to have negative numbers, but maybe we won't get a negative number. I don't know. Let's just try it out, right? We will go, okay. Technically, they're the same index value, right? So 0 of real points refers to 0 in the other one, right? Then can we do, okay. Heap dot heapify. We can heapify real points. Min underscore heap dot copy, right? Let's do min underscore heap is equal to real points dot copy. We put in our min heap, okay? And then we print our min heap. Min underscore heap. Not a built-in functional method. Heapify. Am I messing it up or something? Oh shit, there's nothing in there. Okay, 810. Okay, so let's do... But how can we... Do we need some sort of like dictionary or something? Have a dictionary. We copy the real points, we put it in a min heap, right? But we need... Let's do like... Okay, my underscore dictionary. And is equal to... How to import a default dic. I think I'm cooking here, but maybe I'm not. Default dic integer. Dic ends dot append point. Real points dot add dot. Man, this is way too much code, bro. This is getting. We got our min heap. We heapify. We print the min heap. Then we. Okay, let's do. Well, while k is greater than 0. Okay. We can heap pop. Where's heap pop? We can heap pop. Heap pop min underscore heap. That is our lowest value, right? Let's do num is equal to this. And then we can do, okay, well, my dick num. Let's do, we need a res array, an actual array to return. We can do, okay, well, res.append my underscore dictionary num. I don't know if that'll work. Then we print the res. So we return res. Index is out of range. Bro, why are we getting this index is out of range? So why am I getting an index error, dude? Like, you're getting an index error in this part of your code. Okay. Can we do tuple? Tuple has no attribute append. Oh, that's true. Okay, so how do we get around this? Because this could be multiple. for PT in point list if k is equal to 0. We want to break. Otherwise, we take the value. We take the value and we do res.append point, and then we decrement k by 1. There we go. It's because it was a list of values, that's why. Nice. There's definitely an easier way to solve that. That was a interesting question. Okay, let's check out another problem. Feeling pretty good about heaps, definitely. Take a look at kth largest element in a stream. Should be a pretty straightforward problem. Kth largest element in a stream. We got a 60% acceptance rate. Okay. Okay. You're part of the University Admissions Office and you need to keep track of the kth highest test score from applicants in real time. This helps to determine cutoff marks for interviews and admissions dynamically as new applicants submit their scores. You're tasked to implement a class which for a given integer k maintains a stream of test scores. It continuously returns the kth highest test score after a new score has been submitted. More specifically, we are looking for the kth highest score in the sorted list of all scores. Okay. K and the stream of test scores nums. Int add val adds a new test score val to the stream and returns the element representing the kth largest element in the pool of test scores so far. Kth largest initializes the object with the integer k and the stream of test scores. Okay. Let's import our heap queue for starters. Okay. Here. Heap push. We're just adding a number for this one, right? Adds a new test score val to the stream and returns the element representing the kth largest element in the pool of test scores so far. How do we can build them in heap that contains only the kth largest elements. But I thought we don't really declare it here. We kind of just like do it like this, bro. Right? Let's take a look at Leetcode's video with this one. I'm not too sure how to design this, dude. That's the issue. Okay, kth largest stream. Kth largest element in stream. Leetcode.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem kth largest element in a stream. And it's marked as an easy question, but I definitely feel that it's more of a medium, and maybe that's why many people disliked it. But we are told to design a class to find the kth largest element in a stream of numbers. So stream basically means that we could continue to add numbers to the list of numbers. After we do that, we still have to find the kth largest element now that we've added more numbers to it. And they say that the kth largest element is the kth largest in the sorted order, not distinct. And what they mean by that is basically that if we had, this list of numbers and k equals 3, meaning we want the third largest number. If we look at the distinct values, we'd say, okay, 3 is the largest, 2 is the second largest, and 1 is the third largest. But they say we want to return the kth largest in sorted order, meaning this is the first largest, this is the second largest, and this is the third largest. So we return 2. We're not just looking at distinct elements. If we have multiple copies, we include those as well. The good thing is we only need to implement 2 functions. One is the constructor, where we'll be given the parameter k that we can store, and an initial list of numbers. And this list of numbers, it could be at least k elements, or it could be less than k elements, or it could be more than k elements. So that's something we're going to have to take care of when we do write out the code. But the second function is the add function, where we can actually add a number to the stream of data. And this function is also going to return the new kth largest element every time we call it. So they do tell us that whenever we call this function, we are guaranteed to have at least k elements in the stream of data. So that's good. Good. Even though we might not have k elements when we initialize it, we will have k elements when we call the add function. So now the question is, how can we efficiently solve this problem? Well, suppose we were given this input right in our constructor, this array, and k equals 3. Of course, the intuitive approach is to sort the input so that we can, look through and find the kth largest element a little bit faster. Right, in the original array, we could just scan through the entire input, and that'd be O of n to find the kth largest. But when the array is sorted, though, we can of course use binary search, which will run in log n time. But the problem is, if we want to insert a new value, for example, we want to run add on the value 3. Well, yeah, we can run binary search to add the number as well, we can find where to insert it. But when you insert in the middle of an array, it's a linear time operation, big O of n. So the question is there a better approach? Is there a different data structure we can use? And yes, there actually is. And the data structure that's going to help us the most in this case is a min heap, and we are going to require it to be of size k. And let me tell you why. Well, first of all, a heap is a data structure, if you haven't heard of it, that has a somewhat sorted property. We can add and pop elements from the min heap in log n time. We can also get the minimum value of the min heap in big O of 1 time. Obviously, this is a little bit better than an array, especially an unsorted array like we are given in the input. But the question is, why are we going to require it to be of size k, and why are we using a min heap rather than a max heap? Well, one thing we are going to use to our advantage is that we're only going to be adding elements to our stream of data. We're never really going to be removing anything. So in this example, we're given 4 numbers, but we only need a min heap of size k because we only need the k largest values from the array. In this case, it's 4, 5, and 3. Why is that? Why do we never need the 2? Because we want the third largest value. This is the largest, this is the second largest, this is the third largest. So we have 3 numbers that are bigger than 2. Is 2 ever going to be the third largest value in our stream of data? It's never going to be, because we're never going to remove any of these elements, right? We might add elements. We might add a value like 6. If we add this 6 value, then we don't want to include this 4 anymore. Then we only want to keep track of these 3 numbers, 6, 5, and 8, and now this is going to be the third largest number. 5 is going to be the third largest number. 2 is never going to be included in this group. 2 is never going to be in our min heap of size k. If we added a small element to our stream, like a 1, well, we don't care about a 1. Now, in terms of the code and how we're going to implement this, we're going to have a min heap of size k. First of all, what we're going to do to get this heap is we're going to take this entire input and add it to the min heap, right? So suppose we have 4, 5, and 8 in our min heap. Now we're going to do a while loop. While the size of the heap is greater than k, we're going to pop the minimum value. In this case, the minimum is 2. We're going to pop it. Thankfully, now our heap is size k exactly, so we don't need to continue to pop elements. And remember, our min heap, we can get the minimum value, and since we have these are the 3 largest values, we want the third largest, which is going to be the minimum among all of these. I hope now you can see why we're using a min heap, because we can get the minimum in O of 1 time. But the add function over here requires us to add a value to our stream of data. So for example, suppose we want to run add 3. Well, how do we know if 3 is included among our k largest values? Well, the easiest way to do it, there's multiple ways, but the easiest is just to take that 3 and add it to our min heap. So now we have 4 values in our min heap, and we added it in log n time. Now we want to pop the minimum value from this min heap because we want the third largest value. We have 4 values in the heap. Let's pop the smallest one, which is 3. We can do that again in log n time. And now we want to know, okay, among the remaining, what's the smallest value? Again, it's 4. So as you can see, we can do the add function in log n time. How many times are we going to run the add function? Who knows? Let's call it m. And then this is going to be the overall time complexity of add if we count all the function calls that are made to it. Now, in terms of our constructor function actually generating this entire heap, it's potentially going to be n log n in the worst case. Reason being is we can actually initialize the heap. Like this is our input data. We can turn it into a heap in O of n time. That's not too bad. But then remember, when we started with the array, we had this 2, right? We have to keep popping elements until we only have k elements remaining. So a pop function is going to be log n time. How many times are we going to have to pop? Potentially n minus k times. So this is the overall time complexity. K could be really small. It could be 1. So, worst case, we could have n log n for our constructor. But the add function is just going to be log n. That's a big improvement over the first solution we came up with, which was n time when we were just using a array structure. So heaps definitely help us out a lot. Now we can go ahead and code this up. Now let's code it up. First thing we're going to do is the constructor. You can see I have one comment that hopefully will help guide us in the code. So we can create a member variable with the self keyword in Python. So first we want to create our min heap. And we also want to have another member variable for k, which is going to be the size of that heap, or at least the desired size of it. So min heap initially can just be assigned to nums, and our k is just going to be assigned to the input parameter k. We want to turn this into a heap. Right now it's just a array. We can turn it into a heap in Python like this, heapq.heapify, heapifying this array into a min heap. That will create the sorted property. It will run in big O of n time, but it could be that it has more than k elements. So while the length of self.minheap is greater than k, we can go ahead and pop from the min heap. We can do that with heapq.heap_pop on the min heap data structure. And don't forget the keyword self, since it's a member variable. So the constructor isn't too bad. Now let's do our add function. There's multiple ways you could write it, but the easiest way is just to go ahead and add this value to our min heap regardless of what it is. If it's too big or if it's too small, who cares? We can go ahead and say heapq.heap_pop or heap push to our min heap this value.
I think there's a push pop, right? Yeah, push pop. Push item onto the heap, then pop and return the smallest item from the heap. Runs more efficiently than heap push followed by a separate heap pop. Cool.
And then we're going to pop the smallest value, which might end up being this value, or it might end up being a different value. Who knows? Let's go ahead and just pop it, and our heap data structure will actually take care of that for us anyway. But there's actually just one edge case that you might miss. Remember, our heap might be initialized with less than k elements. This loop will execute if it has more than k elements, which is good, but what if it has less than k elements? Then, if we add a value to the heap, we don't want to pop from the heap if it has less than k elements, or even equal to k elements. We only want to pop if the length of the min heap is greater than k elements. So if it's greater than k, that's when we want to pop from the min heap. But once we've done that, we make sure our heap is valid. It does have k elements. We're guaranteed that when the add function runs. So now we just want to return the minimum from our min heap. And the way heaps are implemented, the minimum value will always be stored in the 0th index. So we can just go ahead and return this. And don't be dumb like me. We forgot to, when we're referencing min heap and the k value, we want to make sure we reference it as a member variable. So let's use the keyword self.minheap. Okay, it looks good to me. Let's run it to make sure that it works. And as you can see on the left, yes, it does work, and it's about as efficient as we can get. So I really hope that this
Okay. It's kind of what I thought. But I just didn't really know how to initialize the value. So if we go, okay, well, do min heap, sorry, heapify. Min heap. Okay. while the length of the min heap of, self dot min heap, so we need self dot min heap, while the length of self dot min heap is greater than 3, greater than k, then we need to pop self dot heap q dot heap pop min heap. We only need the k numbers. Self dot heap q dot heap pop self dot min heap. Got that over here. Self dot min heap. Can get rid of this self heap q. I'm gonna pop it, and we want to check, well, if if okay, then we can pop, right? Otherwise we just want to, what is it, a heap push kth largest object has no attribute heap q. Whoops. Two arguments, heap push expects 2 arguments. And the item, okay. Self dot min heap val. What do you mean k is not defined? K is literally defined here. Maybe we need self dot length. Shit, we're not returning anything. And returns the element representing the kth largest element in the pool. Okay, return self.min heap the zeroth value, which is the top value. Okay. Nice. Simple brute force sorting. K is equal to K. Self.array is equal to sorted nums in reverse. Okay, so the first element. Sorting array inside of add method is redundant. Are you sure it's redundant, bro? I feel like you kind of need it when you after you append a new value, no? So you're just appending to the end of the array. Is this guy hella capping? I don't know. Oh. I think this guy's capping because I think you do need this. Because after you append a value, and append a value, it's only going to the end. Right, and you don't know if that number, what that add's going to be. So... Okay, I'm gonna go to the bathroom. I will be back in a second. We will continue doing some more problems. So I'll see you soon. Yo, what's up, guys? Welcome back. Well, not welcome back. I actually took a nap, so now I'm back. But yeah. Been about, I don't know, it's probably about an hour and a half since I ended that that last video. So I realized, well, new problem of the day came out. So why not? Let's look at that for our next problem. We're always counting some good stuff, so let's take a look. Given an integer array nums and integer k, return the number of good subarrays of nums. A subarray is good if there are at least k pairs of indices I and j, such that I is less than j and array I is equal to array j. A subarray is a continuous, non-empty sequence of elements within an array. The only good subarray is the array nums itself. Okay, I'm trying to understand this problem. Nums 111, 111. K is equal to 10. Output is 1. The only good subarray is the array nums itself. Subarray is good if there are at least k pairs of indices I and j, such that I is less than j and array I is equal to array j. Trying to understand this. There are at least k pairs. At least k pairs. trying to think about this. 314322 that has 2 pairs. Bro, I cannot seem to I cannot seem to understand this question. I have to 2537 count the number of good subarrays. Given an array of integers and integer k. Parent times what is a subarray? You look at every possible subarray and check how many equal element pairs it has. So is it 2 because we have 3, 3, and 2, 2 here? It has 3 pairs, 3. We got 4, 4, 3, 3. That has 2 pairs, 1, 4, 3, 2, 2. Okay. Have at least k pairs of equal elements. How many subarrays? We have 1 here. Okay. There are 4 different good subarrays. So how is this good? Because we only have, or is good if there are at least k pairs of indices I and j such that I is less than j in array I. Four different good subarrays. Man, I'm having such a hard time understanding this problem, like exactly what to do. Feeling confident. duplicate values. For the rate length 5, there were 15 total stories. I feel like I'm not understanding this question fully yet. I feel like I think I'm understanding this problem probably now. But it's definitely still a little bit confusing. Nums. We need at least k is equal to 2. So we look at so equal to right. Maybe import default dictionary. I think it's like this, right? Okay. Actually coincide how ties the math and the logic together. You want to know how many times is not many? Gonna need some sort of res array. Res integer, right? We're adding our count. So you got to count numbers right. I just don't understand how to count these pairs. A subarray is good if there are at least k pairs of indices I and j, such that a is i's s and j. K pairs. Oh my gosh, man. Now it's quick. I was thinking way too much into it. So, okay. So this one is just talking about, okay, if there's all the same numbers, right? Here, we're talking about, okay, this has 2 pairs, right? At least K pairs. Okay, I don't know why this took me so long to see, right? Here, there's at least K pairs, right? We have a 3, we have a 2. That has at least 3 pairs. Two and a 4. So maybe somehow we can count our pairs, right? So we can do like pairs is equal to 0. We can come down here and increment our pairs by 1, right? Because when we see it, we want to increment our pairs by 1, right? And then we want to increment our dictionary by 1, right? Because if we see... Okay. Now we need a classic where we compare here. Well, while our... while our pairs are less than or equal to K. Okay. This is our sliding window portion where we move our left pointer, right? We would check, okay, well... Pairs are less than or equal to K. Well... Wait. While pairs are... if there are at least K pairs of indices. Is greater than or equal to K? Yeah, I think we have to switch this around. Because we need at least greater than or equal to K. Or equal to K. Alright, so what do we do when they're greater than or equal to K? Well, we need to drop it, right? So we would need to check, well, what is our left value, right? So, well... we'd have to do, well, my_dictionary left. Sorry, nums left. Minus or equal to 1. First, we probably need an if statement. We need to check, well, I guess if my_dictionary nums left is greater than 2, we have a pair, right? We'd have to drop that pair by 1, right? So our pairs minus or equal to 1. And then we drop our left by 1 here, right? And then we'd probably need to increment our left pointer, right? So we'd have to go, well, left plus or equal to 1. I don't think I'm understanding this problem fully. Hmm. 34224. How are we counting our res though? Somehow count res, right? So res plus or equal to this. Okay. Yeah, I'm not sure. How am I going? Okay, I was pretty close. I just don't feel like I fully like wrap my head around the problem, right? If I don't fully understand, like I don't understand all the edge cases, how am I meant to, program it if I don't understand all the stuff? Somehow count res. Why are we counting the length of nums minus right? Okay, instead of this, we do pairs minus or equal to MySQL dictionary nums left minus 1. Nums left minus or equal to 1. Left plus or equal to 1. We return res. Index is out of range. MySQL dictionary nums left minus 1. List index out of range. Oh, we got this wrong here. Do pairs plus or equal to. Let's go dictionary. Nums right. Yeah, I'm not gonna submit that. I didn't understand that problem fully. I felt like that problem was really difficult to understand. I'm not gonna submit it though, but because I couldn't do it by myself, but that was tough. Let's check out our Leetcode.io. Did that. Check out some backtracking problems, bro. Let's do subsets. Let's do some backtracking. I feel like we haven't done backtracking in a long time. Like, oh my gosh, dude, what is going on right now? Okay. Well, when do we submit this? Jan 22nd. Integer nums of unique elements return all possible subsets to the power set. The solution must contain duplicate subsets. Return the solution in any order. Okay, so this is definitely a recursive problem. Def backtracking. Right, we want to pass in. Well, we need some sort of result array, right? Because we're returning a list of a list. Result. We need to save our. Probably our cur and passing out nums. Maybe start or something. Integer array nums unique elements return all possible subsets. Solution set must not contain subsets. Return the solution in any order. Okay, so obviously we need to think recursively. Okay, well, our base case, right? So backtrack. We'd obviously want to return our res, right? We need to call our backtracking function. We need to pass in, okay, well, I guess our current status. And then our I guess maybe just our start for now. I guess we can add something. Right. I guess maybe our index too. Index. Maybe passing a 0 or something. Our base case would be okay. Well, if shit. We'd have to check if the current array is inside of our thing. Maybe this has to be a set or a hashy in order to avoid the duplicates, right? We'll check, well, if start not in hashy, then hashy.add start. Can hash sets hold lists? Python. Just want to make sure. Okay. We're definitely going to get a type error, I feel like. Yeah, okay, that doesn't work. Okay. res not in not in hashy. Let's call this cur. If cur not in res, then res dot append cur. Otherwise, we want to our recursive part. Okay, would we want to? Probably want to append, right? Cur.append. Cur.append index, and we want to call our function backtrack index +1 cur. Let's see what that gives us. Low-key. Action recursion depth exceeded. Maybe we need two base cases. We need something to exit the loop, right? Okay, like maybe if the length of cur is equal to the length of nums, then we can just return, right? How are we appending 0? I guess we'd want to start num 0. Append 1, 2, 3. Okay, so this is not working. How can we check if something is in there? Two, three, 1, 2, 3, 1, 2, 3. Next +1. I feel like before we enter this loop, isn't the first thing that we're doing as soon as we call this here is we're appending? Why is it only appending the 3 values? recursive functions really get me, bro. Honestly. We have our res. We append. I know this is our final function, right? Using num0 as a start index, but the recursion should iterate over positions in the list, not the values. You know, exploring both include and exclude files. Yeah, I know that. You're appending index instead of... Okay. Code out append nums index, backtrack index +1. We get to a value. Oh my gosh, dude. Maybe never reaches this. Maybe this has to be the first thing that we have to look at, right? Because we need to get to our topmost, right? We need to get to 1, 2, 3, and then we need to come back after, right? So code.append. Sorry. Code.append. Code.copy. Right? Zero, 1, 2. Sorry, nums index. Is it actually getting in here? Friend. Okay, so it does get here, right? Res.append code.copy. 1, 2, 3, 1, 2, 3, 1, 2, 3. Why is it printing like that? Okay, so what we're doing here is we're calling this backtracking function. We start with an empty array. We get through here. Okay, does it equal to the base case? Well, no. Then we go to our recursive function. We append the next value. We append the value that we're currently at. Then we increment the index. We go here, append the value, increment the index. Append the value, increment the index. Then we reach here. We append the copy, and we backtrack back, right? So it should just print 1, 2, 3 here, I think. Yeah. Okay. Including the subset, excluded from the subset. Okay. For subsets, each element can be either included in the subset or excluded from the set. Your current code only includes nums index and cursors, so you're missing half of the possible subsets. Your base case is too early. You're stopping when length cur is equal to length nums, but not all valid subsets have to be full length. You want to stop when index is equal to length nums, i.e. when you've considered all elements. Index is equal to length nums. Okay, so we got to this part here, right? Dependent nums index, we increment by 1, right? What we miss is we need the exclude, right? Okay, so if we have the include, now we would exclude. So we do, okay, code up, remove that element, and call the backtracking function. Index plus 1, okay. That's all we were missing, just here we call the backtracking function, right? We get all the way to 1, 2, 3. Base case, add 1, 2, 3 to res, exclude 3. Then we go through here, we pop 3. Then we call the backtracking function. Man, we were so close. It was just that exclude pile was a little confusing. Frustrating. Let's jump through the subsets one. We've done these two, right? Got a heap priority queue. Yeah. Graphs. We're definitely going to get back to that. Okay, I'm going to call it there for today. We've got about 2 hours, so I appreciate you guys watching, and I will see you tomorrow.